Welcome to Analog Devices. This course is primarily about operational amplifiers, also called op-amps. Now, op-amps are constructed using the circuits that we learned in semiconductor devices. At the front end of an op-amp is a differential amplifier, which amplifies the difference between two inputs. The output from the diff amp is fed into more stages of gain, which is accomplished using one or more CE amplifiers. And then out of the CE amplifiers, that output is fed into a Class B push-pull emitter follower, which acts as the final output that can drive a relatively low resistance value, so it can provide a current boost. And if you remember that one had an upper and a lower transistor, where if the upper transistor turned on, current went out, and if the lower transistor turned on, current came back in. The output of a differential amplifier, what it is amplifying is, here it has two inputs, and what you get on the output here is the difference between the inputs multiplied by a gain factor. So the output is equal to the gain value times the positive input subtracting the negative input. And another way of saying that is V out is a multiple of the voltage difference between the two inputs. If you take a look at what's inside an operational amplifier, you'll see some of the circuits that we studied in semiconductor devices. At the front end, you have a differential amplifier, which is formed by these two transistors, and the input to this transistor is called the non-inverting input, and this one is called the inverting input. In operational amplifiers, we use one output, which comes off of the non-inverting transistor, and that goes into a second stage, which has two CE amplifiers, which kicks the gain up quite a bit. This is where all the gain comes from in an op-amp. The output of the CE amplifier drives the final stage, which is a push-pull Class B amplifier that has an upper and a lower transistor, and when the upper transistor turns on, the circuit pushes current out to the load, and when the lower transistor turns on, it pulls current back in and feeds it to the negative supply. So why is this called the non-inverting input and this one called the inverting input? Well, if you remember from semiconductor devices, when we talked about diff amps, we said that if we put a signal in on the base of a transistor, so if we put something on the base of this transistor, it comes out off of its collector out of phase. So a signal applied to the non-inverting input appears to be out of phase going into the CE amplifiers. The CE amplifiers also have a negative gain, so they will flip that back over again and it will be in phase with the original input. The push-pull amplifiers do not flip the output. They have a gain of +1, so over here, if we put a signal in, we will see that signal coming in phase with the original input, and that is not inverted. However, if we put a signal on the inverting input, that goes into the base of this transistor, and if you recall, that is a common base connection, that will appear in phase with the original signal at this point. That will be out of phase at this point, and then out of phase coming out of the final output. So if you put this signal in here, it comes in out of phase on the final output. So that is the inverting input. Now, obviously, we're not going to draw all of those transistors every time we want to put an op-amp in a schematic. So there's a schematic symbol, which is a triangle, which is kind of the simplified version of describing an op-amp. So every time you see this triangle, you can assume that there's a diff amp and some CE amps and the push-pull amplifier inside. Now, the triangle symbol has as well a positive input and a negative input, which is connected to the non-inverting and the inverting input. And it will always have an output, which comes from the push-pull amplifier. It may have the power supply line shown, which goes to a positive voltage and a negative voltage, although they are not always shown, as sometimes it's kind of obvious where that comes from. The mathematical symbol for analysis, well, that's your standard two-port model, where you have two different voltages being applied to the input of the op-amp, and that goes to a input impedance shown as Rin. It's a dependent voltage source which has a gain factor which multiplies the difference on the input voltages by the gain factor. That amplified voltage is delivered to an output load through a finite output impedance, which is shown as a series resistance here. So to give you an idea of what those values are, Zin is very high in an operational amplifier. It's in the megohms. In fact, it's high enough that usually we will consider that an open circuit. So usually we will think of the input of an op-amp basically as being open. Well, if it's an open, that means that no current flows into the input. Now that's on an ideal op-amp. The perfect op-amp, there's no current flowing into the inputs. But in reality, it can be a couple of picoamps. So it's almost no current. The gain factor, well, that's very high. How high is very high? It's someplace between 100K to 200K or more. Those are on the low values. Z out, the output impedance, is low, but it's still not zero. You can expect an output impedance to be about 25 ohms when we're not using feedback. Using the characteristics of an op-amp, we can come up with a couple of simple rules for analysis. So remember that the differential amplifier, the output of the differential amplifier, is going to be some multiple of the voltage difference between the inputs. So it amplifies the difference between these two inputs by 100,000. So we can say that V out is equal to AV times the positive input minus the negative input. That is the difference between the two voltages. So if the gain is really, really big, what we can say is that if the positive input is greater than the negative input, then what's going to happen is the output voltage is going to swing up. On the flip side, if the negative input is greater than the positive input, then the output is going to go down. So what's that saying is that if the inverting input is bigger than the non-inverting input, then the output is going to swing down. Now, I kind of like to put that into a basic rule that basically says the output will swing in the direction of the input that is greater. So if the non-inverting input is greater, the output swings up. If the inverting input is greater, the output swings down. Another quick little design rule for op-amps is that the output cannot exceed the supply voltages. It can only come close, and close depends on the part. For example, if you're using a 741 op-amp and you're using it with a supply voltage of plus minus 15, you're only going to get an output voltage on that 741 of about plus minus 13. When the upper and lower transistors turn on, they are not perfect shorts. They have a little bit of a voltage drop across them, which means you're not going to get the 15 volts out. So just because the V out of an op-amp is AV times the voltage difference, okay, so it's AV times the voltage difference. Just because the gain is 100K and the voltage difference is 1 volt does not mean that you're going to get 100,000 volts out of this thing. You're not going to get any more voltage out of it than what it's being powered by. Okay, so let's run through a couple of short snappers here just to make sure we got the idea. So assume that the gain here is 10 and that V out is the gain factor times the difference between the inputs. So if I come along and I say, well, if it's 2 volts and 1 volts, what's the output? Well, that becomes 2 minus 1 times 10. So the output would be 10 times 1 volt. You would have 10 volts. Okay, how about now 1 volt and 2 volts? So V out equals 10 times 1 minus 2, because it's the positive input subtracting the negative input. So that would be minus 1. So we would have an output of minus 10 volts. So what about if one voltage is positive and one voltage is negative? Well, V out is 10 times the positive voltage, subtract the negative voltage. So the difference between the inputs is 4 volts. So that would give you 40 volts out. That is if the op amp is powered with something like plus minus 50 volts. Otherwise, it would hit the rails and you'd probably get the 13 volts out. So the answer here, if it's an ideal op amp, is 40 volts. Okay, well, what about if it's 1 volt and 0 volts? Well, that would be 10 times 1 minus 0, so you would get 10 volts. Okay, so what if the output is really large, like the gain is really large? Let's say the gain is 100,000 and it's powered by 15 volts and minus 15 volts. What would we get then? So if this is 2 volts and 1 volt, the difference between them would be 1 volt, and we would get 100,000 times that. So V out, the op amp would try and drive it up to 100k volts, but of course it would never get there. So you would get about plus 13 volts depending on the op amp. Okay, same situation, but now it's 1 volt and 2 volts. What are you going to get? Well, that would be 100k times 1 minus 2. That's minus 1. So it would try and swing down to minus 100,000 volts. It wouldn't get there. You would get minus 13 volts. Okay, well, what if you put the same voltage? What if you put the same voltage on both inputs? Let's say 1 volt. Well, if V out equals AV times V plus subtract V minus, that would be 1 volt minus 1 volt. So the difference between the two inputs is 0 volts. Well, 100,000 times 0 is still 0. So out of this, you should get 0 volts. Bear in mind that sometimes on the input transistors, on the inputs here, sometimes there's minor little differences on the input transistors. So although you're supposed to get 0 volts out, you might get a couple of millivolts in either direction, plus or minus 10 millivolts. This is called a common mode input. So when we put the same thing on both sides, we call that a common mode input because we're putting a common signal to both inputs. Okay, so let's say now the gain is 100,000. Is there any way we can put a voltage on here that we don't swing off to the rails? And I think that if you put 1.00001, what is that? 1 volt and a microvolt, and 1.00000 volts here, you'd have a microvolt difference between the two inputs, which would be amplified 100,000 times. So if you did that, you would get 0.1 volts on the output.